Imagine you are standing on the 89th floor of one of the tallest skyscrapers in the world. Outside the glass, the wind is screaming, and you can actually feel the tower of steel beneath your feet start to move. It isn't breaking or falling, but it is swaying back and forth like a massive tree caught in a storm. The strange part is that engineers designed the building to move this way on purpose, and the device they use to control that sway? It weighs more than 100 fully loaded school buses, and it just hangs there, swinging silently in the dark. To keep that sway under control, they hide a clever device deep inside the structure that uses movement to stop movement. It is a wobble designed to cancel out a wobble. That is exactly the hidden logic we are going to break down today. Most people assume skyscrapers are rigid objects, bolted to the ground like fence posts, but the reality is far more flexible. These structures are designed to bend slightly in the wind because a perfectly stiff building would crack and snap like a dry stick under pressure. Think of a tall tree during a thunderstorm. It survives because it can bow and flex, and engineers use that same principle to keep skyscrapers standing. But this necessary flexibility creates a dangerous side effect. Every tall building has a natural frequency, a specific rhythm where the structure likes to sway. Wind never blows in a perfectly smooth stream. It hits the glass in pulses that act like a person pushing a swing. If those pulses hit at exactly the right moment, the energy doesn't dissipate. It builds. Engineers call this resonance, and it means every sway becomes slightly larger than the one before. To picture this, imagine carrying a full tray of drinks across a crowded room. If you walk with a random gait, the liquid wobbles and settles. But if your footsteps accidentally match the natural sloshing rhythm of the water, every step adds more energy to the wave. The wobble grows until the drinks spill. In a skyscraper, that same energy buildup can cause structural damage or make the people on the top floors feel seasick. Here is a fact most people never hear. One of Manhattan's most famous skyscrapers was quietly fixed in the middle of the night while thousands of people slept inside it, because the engineers had discovered it could fall down. We can see how serious this is by looking at a famous near disaster involving the Citigroup Center in New York City. Built in the 1970s, it sits on 4 massive stilts at the center of each side, rather than the corners. That bold design created a hidden vulnerability nobody caught until the tower was already full of workers. An engineering student running her own calculations discovered the building was dangerously weak against quartering winds, gusts that hit the corners at a 45-degree angle. The original tests had never checked for that direction, which meant the building could reach resonance far faster than the designers imagined. Once the lead engineers ran the numbers, they realized the risk was real. They had a fully occupied skyscraper in Manhattan that could fail in a major storm, and they couldn't tear it down and start over. Crews worked through the night to bolt diagonal steel braces into the structure. As a final layer of protection, they added a tuned mass damper, a 400-ton block of concrete and steel sitting on giant springs. This weight was designed to push back against the building's sway, absorbing the wind's energy before it could build to a breaking point. The fix worked, and it proved a core concept in modern engineering. By using a correctly tuned mass moving opposite to the wind, you don't fight the energy, you cancel it out. If you want to see more of how the world works, hit subscribe. Now let's look at what the solution looks like when engineers build it as a deliberate feature from day one. Not an emergency fix, but a core part of the design. What if the only thing standing between a 500-meter tower and a catastrophic collapse was a single golden ball, slowly swinging back and forth like a giant pendulum? Welcome to Taipei 101 in Taiwan, which held the title of the tallest building on Earth for many years. It stands 508 meters tall in a city that deals with constant earthquakes and massive typhoons. Go between the 87th and 92nd floors, and you will find a massive object spanning 5 full stories, unlike anything else in the world. It is a golden steel sphere weighing 660 tons, roughly the size of a small house. It hangs from the ceiling by thick cables and is the tuned mass damper for Taipei 101. Most engineering solutions hide behind walls, but this one is on display for visitors to watch as it moves. The sphere is tuned to sway at the exact same frequency as the building's natural rhythm, but in the opposite direction. When the wind pushes the building right, The ball is already swinging left. When the building tries to push back, the ball moves the other way. Think back to that tray of drinks. Imagine someone walking beside you, holding the other end of the tray and moving it in the exact opposite direction of every wobble. Every time the tray tips, they push back to level it out. That is exactly what this sphere does. It doesn't swing freely, though. It is attached to heavy hydraulic cylinders that work just like the shock absorbers in your car. They take motion and turn it into heat, which pulls the energy right out of the system. The result is a building that stays steady while the storm rages outside. If you want to see more of the hidden logic behind the world's biggest machines, hit subscribe. We take apart the complex world one mechanism at a time, and there is plenty more to come. The sphere inside Taipei 101 is a masterpiece, but it has one real limitation. Engineers tuned it at the factory for specific frequencies, and because it is a passive weight, those settings never change. It works perfectly for the conditions it was built to handle, but the real world is rarely that neat. This is where the Shanghai Tower comes in. Standing at 632 meters, it is the second tallest building on Earth, and it uses an active mass damper. The sphere in Taipei just reacts to the wind because physics forces it to move. The Shanghai system has a brain. Sensors and computers read how the building is swaying in real time and drive the damper mass to exactly the right position at exactly the right moment. The Taipei system is like a good shock absorber. It handles bumps automatically. The Shanghai Tower is more like a driver who sees every dip coming and steers around it before the car even gets there. That ability to adapt makes it effective across a much wider range of conditions. Then there is One World Trade Center in New York, which takes a different approach entirely. Instead of a swinging pendulum, the engineers built viscous fluid dampers directly into the steel structure, thick cylinders filled with a special fluid that resists movement and absorbs energy. Same core logic as the hydraulic cylinders in Taipei, but spread across the whole building instead of concentrated in one giant ball. Here is the part that blows most people's minds. The Shanghai Tower's damper system has sensors so precise they can detect the building moving less than the width of a human hair and correct for it in real time. The physics is the same no matter the shape. Whether it is a sphere or a row of cylinders, the goal is always to convert movement into heat and bleed the energy out before it builds up. Every super tall going up today has some version of this because it is not a bonus feature. It is how the building survives everything from a once-in-a-century storm to a regular windy Tuesday. The buildings that look the most solid are the ones quietly moving on the inside. That movement is controlled, deliberate, and precise. Right now, the wobble that cancels the wobble is running in towers you have probably walked past without ever noticing. If you want to see more of the hidden logic behind the world's biggest machines, hit subscribe. Share this with someone who would never guess a skyscraper works this way, and I'll see you in the next breakdown.